It's like community engagement.
Is
Technical skills.
that's their challenge part, or that's mostly where they're working?
And that's what the jobs are requesting for, how many people have. They're basically requesting for skills you can only get by working, is what I understand best. No, the survey at the end, we don't reason that, it's just, it just sends out like to all practical professionals when they have questions. Okay, what's the job title, what's your area, job function, director, executive, manager, whatever. No, it's just in the city.
All right, we're live. And everything is loaded. How are you all doing today? Recovered from Thanksgiving. I think I'm not going to eat anymore this week.
Yeah.
All right. Oh, look at that. I think that when someone types in a question, we should hear it. So don't be shy, folks who are online, about asking a question. All right, well, so after the exam last class, we covered analysis of variance, a big topic on its own. Just one class of that. It's just a kind of a teaser. And now we're doing something completely different, which is kind of going to be another teaser, analysis of two categorical variables. Categorical data analysis is a big topic and has a lot of special techniques for it, and something that you do a lot of in epidemiology. So So we're going to cover the Pearson chi-squared test and looking at 2x2 tables. In general, Pearson chi-squared for any size of a table, but looking a lot today at the 2x2 table where the risk ratio and odds ratio are defined. And I'll mention a couple alternatives to the chi-squared test. So here's a motivating example. An interesting one from a study back in 1991. I don't know if any of you had a chance to take a look at it. I managed to post it first thing this morning into Blackboard. But it was a study of race and the death penalty in Florida, where these researchers had managed to examine every case where an individual was convicted of capital murder, or of first-degree murder, which is punishable in Florida by the death penalty, and then counted how many of those cases had resulted in the death penalty, and specified as a predictor variable the race of the defendant as black or white. So they had about 10,000 cases. Here's the 2x2 table. So the basic two variables are whether or not the death penalty was given to that defendant, and the race of the defendant. So overall, about only 364 out of about 10,000, so about 3% were given the death penalty, and they were about half and half, the races of the defendant, black or white. And the question motivating the study was, does there exist evidence of discrimination in the death penalty verdict? Or talking about it statistically, probabilistically, is the death penalty verdict independent of the race of the defendant? Hello?
Question.
Yep. Question?
Why would you want to do statistics on that?
Why would you want to do statistics on that?
You can kind of clearly see there's a difference. So I guess what more information could you be giving by saying, oh, this difference is statistically?
Well, imagine, so there is a fairly big difference there, and there is more to this data set than just this table, which I'll show later. But even with just this table, you could imagine if there were a difference between like 236 to 230, you don't know if that is just a variation that you would expect even under a null hypothesis of no difference, or whether that is incompatible with independence between race and death penalty verdict. So the purpose of doing statistics, first of all, descriptively, is to put it into more interpretable terms than just counts, and then for inference, saying whether or not the data are consistent with the null hypothesis. So, like all the other hypothesis tests, we've got the null hypothesis, which is of no difference. So the null hypothesis is independence between these two variables, or put another way, that the probability of receiving the death penalty is the same for white and black defendants. And the alternative hypothesis is that there is a difference. So this is, it's a little bit different, but it's the same idea as all of the other hypotheses that we've been writing. So we could take a proportions approach, and you've learned how to do that already, where you would write down the proportions of death penalties for white and black defendants, and test the null hypothesis of no difference in those proportions, using the normal approximation and doing a two-sample z-test, or constructing a confidence interval for the difference in the proportions. And you could do this. This is a valid approach. What I'm going to show you today, this contingency table, is a little bit more general than that, in that it's not limited to cases where you can express your data as a proportion. So if you have 3 different options, it's not so simple to just express a proportion. The frequency table approach works on any size of contingency table. So the basic approach here is we're going to write down the number of counts that we would expect in each of those cells, calculate the difference between what we observe and what we expect, and then get a test statistic from that we will be able to compare to a distribution under the null hypothesis. Sound familiar? So let's build up those expected counts. If they are, if race of defendant and the death penalty verdict are independent, we can write down exactly how many we would expect in each of these cells. So we can start on any cell here and use the probability that you learned early on to start writing in expected counts. So just the probability of receiving a death penalty is 364 out of 10,068. So you get a probability from that, and the probability of the defendant being white is 4,909 out of 10,068. And you remember then how to calculate this probability of both of those being true? So you have two probabilities: death penalty, yes; race, white. How do you get the probability of a random individual in this study under the assumption of independence being a white defendant who received the death penalty?
You just multiply the two probabilities if they're independent.
That's right. You just multiply the two probabilities if they're independent. So that's what's done here. You multiply those two probabilities, you get a probability, you multiply it by this total, and you can fill in 177.5. So that's what you expect under independence. You could continue doing that for the whole table, calculating those probabilities, multiplying out. You don't need to, because we know the totals in each of these. So how many do we expect in this, just using subtraction? Yeah, the rest of it, 364 minus 177.5. That's it. So this actually relates to the degrees of freedom, where when you're given the margins, it is how many that you can fill in just using subtraction. So in the 2 by 2 case, once you have one of them filled in, you can fill the rest in just by subtracting from the margins. So there are there are rows minus 1 times columns minus 1, which is just 1. There's only 1 degree of freedom here. So once you have one of the cells, you can reconstruct the rest. So going ahead and filling these in, this is what the null hypothesis looks like. So far, so good. Now, from these two tables, from what we've observed and then what you've calculated as expected, the chi-squared statistic is pretty straightforward to calculate. This is a new statistic. We've so far used the Z statistic, which was the standard normal distribution. We've used the T statistic, which has, there's a different distribution for each number of degrees of freedom. We've used the F statistic, which actually had numerator degrees of freedom and denominator degrees of freedom. And this is now our fourth statistic, the chi-squared statistic. And it just has, and there's a different chi-squared distribution for each number of degrees of freedom. So in this example, we're going to use a chi-squared statistic with 1 degree of freedom. We use this Yates correction. It's a little bit more accurate for 2 by 2 tables. In reality, we often use software, and it will do that anyways. But it's good to know about. So you can see a pattern in how this hypothesis test go. These hypothesis tests go, right? In every case, we write down a null and an alternative hypothesis. We calculate a test statistic, and if the null hypothesis is true, we know what the distribution of that test statistic is, and then we just compare the test statistic that we got from our sample to that null distribution of the test statistic and calculate the probability of observing what we observe or something more extreme. And that's a common theme for all of these hypothesis tests. The chi-squared test, like the F test, we will only ever use the right tail. Can someone explain to me why that is? What's going to happen as you depart from from the expected counts in a table, what's going to happen to chi-square? Yeah, it's going to increase. No matter how you depart from the table of expected counts, chi-squared is going to increase, which makes it a one-tailed distribution. The only way you could end up, what's the only way you could end up with an improbably small probability under the left tail? What's that? Yeah, if you make them more similar than you would expect by chance, possibly by falsifying data. So you could imagine if you have 10,000 subjects, 2 groups, your chances of getting exactly the same proportions in both groups might be pretty small. So, but for departures from the null hypothesis, chi-squared only gets larger. And just to look at this again, that's because the more difference there is between your observed and your expected values, it's the sum of squares of these differences, and so that can only increase. This value is always positive. The smallest you could ever get for chi-squared is 0 if your observed matched the expected counts exactly. So if our sample is consistent with the null hypothesis, we get a relatively small value of chi-squared, we will not reject the null hypothesis of independence. If there is an association between those variables in the rows and columns, then those differences between the observed and the expected counts get larger, chi-squared gets larger, and it becomes less and less probable that the value of chi-squared from our sample is from that null distribution. And when chi-squared is sufficiently large, so there's probably a less than 5% probability of observing the value of chi-square that we see, or something more extreme. So under the right tail of the chi-square distribution, we'll reject the null hypothesis and instead accept the alternative hypothesis. So the alternative hypothesis is inherently two-sided, meaning that there's no directionality to the alternative hypothesis. The alternative is just that that these two variables have dependence, they're not independent, but we will only use the right-hand tail of the chi-square distribution. So that's a difference from the t and the z distributions, but a similarity with the f distribution. We have a few assumptions. Like all of the tests, we assume that the observations are independent, that we have a representative sample of our population. There's an assumption of a large sample size for the chi-square distribution. It is based on an assumption of the chi-square distribution occurs under a large sample size. So here's some rules of thumb. We shouldn't have expected counts of less than 1, and no more than 20% of the cells should have an expected count of less than 5. If this is not the case, the p-value from chi-square test does not tend to be off by a lot. So if you have 10 to the minus 5, you're going to reject the null hypothesis no matter what. But for a marginal test, 0.04 or something, the p-value is not exact from the chi-square test. It's based on a normal approximation. For small samples, then the correct distribution to use is a binomial distribution, which is oddly difficult with a number of software packages, and I think is the only reason that we don't cover it usually in intro biostat. I mean, we did cover the binomial test or the binomial distribution earlier on, but I'm going to mention another alternative later on, Fisher's exact test, which is often offered by every software package and is easy to do, but it's for a somewhat different problem, and I'm not sure exactly why it ends up being a substitute for the chi-square test, but I'll talk about that later. Unlike the t-test and the z-test, we're not making an assumption about the population distribution, so there's no assumption of normality or whatever on the population. Of course, this is just for categorical data, so for a binary variable, it doesn't mean much to talk about a distribution anyways, other than the proportions. For a categorical variable with more than 2, you could talk about the distribution, but there are no assumptions involved in that for the chi-square test. Okay, so doing this calculation, just subtracting these 236 minus 177 squared divided by the expected 177.5, adding these up over all 4 cells, we get a chi-squared value of 39 and a p-value of something very small. So as you were able to see just from the first page, the independence is clearly not a reasonable, it's not reasonable that these variables came from independent variables, or that this sample came from independent variables. So we reject the null hypothesis. What does that mean? So since it's a inherently two-sided test, doesn't tell you about where the departure from the null occurs. It just tells you that they're not independent. But looking at the proportion of death penalty verdicts among white defendants, it's 4.8%, and among black defendants, 2.5%. So based on these data, it would appear that the white defendants are more likely to receive the death penalty. Not what I would expect based on what I know about history of the US, but I think there is more to it that the paper gets into, and we'll get into as well. Questions so far? Pretty straightforward. Thumbs up. Okay. But we'll get to that later, the conclusions and whether there is what more there is to it. I want to introduce relative risk and odds ratios to you, something that you no doubt will learn about and use at length in your epidemiology classes, but I want to introduce to you. So risk ratio is perhaps the more intuitive measure. So first, a risk. In this case, the risk would be the probability of receiving the death penalty. That's the risk. So you've been convicted of first-degree murder. What is the probability that you will receive the death penalty? That's the risk. The risk ratio would be that risk for, in this case, we're going to put the white defendants on the numerator and black defendants on the denominator, and it is that probability, 4.8% divided by 2.48%, 1.94. So risk ratio is a ratio of two risks. Now, odds is something that I guess is familiar to people who bet, but isn't familiar maybe to a lot of other people. Odds are the chances of something happening to it not happening. So instead of on the for the risk or the probability on the denominator is the total number of events. Whereas with odds, the denominator is the complement of what's on the numerator. So instead of being probability over n, it's probability over, or instead of just probability, it's probability over 1 minus probability. Question? Yeah, it's arbitrary. You could put either one on the numerator. It's common to put if you have a placebo or a reference group, that you would put them on the denominator, whereas and put your treatment or your exposure on the numerator. In a case like this, it's really arbitrary. It might be a little bit easier to read and understand putting it in the way that you get a number that's greater than 1. So if you put black on the numerator here, black defendants on the numerator, white defendants on the denominator, then this would just be 1 over 1.94, so about a little over 0.5. But it's arbitrary. So the odds ratio is just a little bit different, 1.98. The take-home message from that is that in cases with low probabilities, risk ratio and odds ratio are almost the same. So this denominator of 1 minus p, in this case, is, well, instead of, so each of these, instead of this being 0.048, it's 0.048 divided by 1 minus that, but this is like 0.95. So dividing by 0.95 doesn't change that too much. So risk ratios and odds ratios are very similar for low prevalence events. For high prevalence events, they're quite different. So take like the example of rolling a die. What's your risk of getting a 1? Yeah, 1 out of 6. And what are your odds of getting a 1? What's that? Well, I'm not talking an odds ratio or risk ratio, just the raw odds or raw risk. So the risk is 1 in 6. What are the odds of getting a 1? Nope, that's the risk. 1 to 5, that's right. So the risk is 1 in 6, the odds are 1 in 5.
So the 1 minus p is the odds?
The odds are the probability of something occurring divided by the probability of it not occurring. The risk is just the probability of it occurring.
Oh, so it occurs 1 time, then it doesn't occur
Right.
5 times.
Right. So the odds would be 1/6 divided by 5/6, or 1/5. Yeah. And then when it's, when it's 200 out of 5,000, it doesn't make a lot of difference. When it's 1 out of 6, it makes a pretty big difference. So you could calculate the the risk ratio, say for getting a 1 compared to getting a 2 or 3. That would be 1 out of 6 divided by 2 out of 6. So it would be 50% would be that risk ratio. But then the odds ratio would be 1/5 divided by 2/4. So it would be 2/5. So it would be 40% instead of 50%. So there's a fairly substantial difference between the odds ratio and the risk ratio in the dye example. How's everyone feeling about odds ratios and risk ratios? You'll get lots of it in EPI. More of it probably in EPI than biostat.
So if you were to read that odds ratio calculation as a sentence, how would you read that?
Good question. So I would read this as saying, it'd be hard to do it without saying odds ratio. The odds ratio of receiving the death penalty for white defendants compared to black defendants is 1.98. So the odds of a white defendant receiving the death penalty are 1.98 times larger than the odds for a black defendant.
Did you say that the probability of white people getting the death penalty?
So you want to say the probability of white defendants receiving the death penalty is some amount. Tell me what amount higher than the probability of black defendants receiving the death penalty. Fill in the numeric blank.
In our EPI class, I think Dr. Jones said that we should not use higher or lower. It kind of messed up the ratio. So she usually just asks us to say has 1.98 times of the odds compared to, you know.
Just so that you're not thinking that it's additive. Yeah. 1.89. Maybe there's less. Yeah, maybe there's less chance of confusing someone that way who is not familiar with what an odds ratio means. Is 1.98. Times as likely.
No, but that would be the risk ratio.
Yeah. So what you were getting at was the risk ratio, the way you would read that.
I love if you could say that in a sentence without saying that the odds ratio
Right.
is that.
So the odds of a white defendant receiving the death penalty are 1.98 times the odds of a black defendant receiving the death penalty. But it's hard to say it without saying odds, because odds takes some definition to say what it means. Really, what you're getting at is risk ratio is actually a more intuitive measure, because this you can read as white defendants are 1.94 times as probable or as likely to receive the death penalty. So yeah, odds are, it's not a super intuitive measure. They're the ones that we end up using in most statistical tests. We often use risk ratios in descriptive statistics because they're the more intuitive measure. But in logistic regression, we use the odds ratio just because it's convenient statistically. Oops. Another reason for using the odds ratio is that there are these two different ways of calculating it. So going back to a more typical public health scenario with disease, healthy, and exposed, unexposed, it could be the probability of disease given exposure divided by the 1 minus that probability. And then on the denominator, probability of disease given that you're unexposed divided by 1 minus that. The second way has these reversed, so the probability of exposed given disease. Anyone want to make a guess about how these two are related? Yeah, question?
Like sensitive,
What's that?
like, it's like defining PPV versus sensitivity. Well, it's not taxable.
The relationship between these two calculations does have to do with that same kind of a difference. Of course, probability of disease given exposure is related to probability of exposure given disease through Bayes' rule. And this is sort of your basic definition of odds ratio. This is one that it is related to via Bayes' rule. Now, in a case control study, which are we going to know here? What's that?
Just the exposure.
We'll know well, in a case control study, we're controlling, we're controlling the proportions of disease and non-disease in a way that we will know the probability of disease for the exposed group and for the unexposed group. The probability of exposure given disease, we will not know. Right. So, whereas with the risk ratio, there's only one way to estimate it. And probability of disease given exposure, this is something that we can't estimate from a case control study. So that is another reason for sometimes using odds ratio. But in a representative cross-sectional study where the probability of exposure is the same as it is in the population, we could calculate a risk ratio. Yeah.
I think, I don't know if I remember it wrong. I think when we say that there's a large population that you're collecting in the case control study, you can actually interchange these two calculations. It basically, oh no, not calculation, but when you interpret it in the end of the study, you can either say it's exposure over disease or disease over exposure. The odds ratio if there has a large population in the case control.
Sorry, could you say that again?
I don't know what I'm saying. Yeah, like it doesn't matter in the end. Like if you have a large population of the study population.
If you have a large study population, then
in the end of the odds ratio, you can interpret it as a odds ratio of the exposure over disease or disease over exposure. It doesn't matter anymore.
exposure to disease. So let's look at this again.
It kind of cancel out, become an AC over BD. That's.
So are you talking about a case control study?
In a case control study. Because usually in case control study, we're saying that probability of disease overexposure, right? So you have, say like you have this disease, you develop this disease has, with this exposure has 1.98 times of odds comparing to the other unexposure, right? But if you have large study population, then you can say that you will develop this disease has 1.98 times of the odds.
Yeah.
Whatever. Just like,
Just looking at this slide from our epic class.
Yeah.
Exposure odds ratio equals
It's
disease odds ratio.
Which I think is what you're saying here. It's the same thing. So odds of exposure given disease is equivalent to the odds of disease given.
Okay, so it's just talking about these two equations,
Right.
but-
It's the same thing. It's just.
right? But what I said is still true, that from a case control study, no matter how large, you can't say what the probability of exposure given disease status is. That's not
because you control the disease.
Right.
Enter the study.
right.
But when you, in the end, in your conclusion, you can say either way. Which you said in the
That's,
first
yeah,
slide.
that's what
So the probability,
I remember when I did
yeah.
the second homework.
Yeah. That's dependent.
Yeah, it has to be a large pool study population.
Thing is, the probability of exposure given the disease will even given the same say risk ratio, or the same risk of disease from an exposure, then the probability of exposure given disease will vary with the prevalence in the population. So it'll be different for a low prevalence population than it is for a high prevalence population because of that Bayes rule association between these two variables. Let's see, so suppose we have an exposure that, I'm not sure I'm going to be able to come up with an example on the fly here, but I'm going to try. We have an exposure that increases your disease risk tenfold. So, so your risk ratio is 10. Now, or let's put it this way: among the exposed population, the probability of diseases is 50%, and among the unexposed population, it's only 1%. So the risk ratio then is 50. Now, in a case control study where we have 50-50, what is the probability of exposure given that you have the disease?
I think that's the big thing, is just that if you're doing case control, you're not looking for the disease. That's not what you're trying to measure. So like, even if you can get a quick way, you're trying to measure the exposure. The corporate study, you're trying to figure out what's the disease. That's the big difference. One is measuring disease outcome, one is measuring exposure. And that's just, between case control and cohort. Even though you can't calculate both, it just doesn't make sense to calculate one when you're looking at one outcome versus the other.
Yeah, so what I can tell you is that in a very low prevalence population, your probability of exposure given that you have the disease is going to be lower than in a high prevalence population. So, and that's, I mean, I'm thinking of it in terms of Bayes rule, which is because in Bayes rule, your probability of exposure given the disease is the other one probability of disease given exposed times the probability of exposure. So so it depends on that prior probability. But so the message, the take-home message from this is that in a case control study, we can use this equation to, we can use this second version to calculate the odds ratio, but we don't have a way to do it for the risk ratio.
I thought it was OR1. And OR2 was cross-section?
I think actually it's OR2 for the case control because we're controlling how many disease and how many non-disease. So we can calculate the probability of exposure in each of those groups.
So is it, did you say it's odds of exposure for case control?
Yes, this is the odds of exposure among your diseased population and among your non-diseased population. Whereas in a cross-sectional study, we would look at the probability of disease in exposed versus unexposed populations. So yeah, that was off the top of my head. This is right. Both can be calculated in a cohort study. Whereas odds ratios can be calculated. Both can be done in a case control. In a case control study, you can still calculate odds ratio, but you can't calculate the risk ratio because it depends on the prevalence of the disease. So if you know the prevalence of the disease in the population, you could use Bayes' rule and still get a risk ratio. But it does depend on that prevalence. Oh, and they're sorry, they're
exactly the base rule exactly explains what's going on, why we can use that interchangeably.
sorry, Bayes' rule explains how you can use them interchangeably as long as you know the prevalence in the population. So the case control study doesn't tell you anything about prevalence. So, but if you know the prevalence, you can use Bayes' rule, you can calculate the risk ratio. And of course, if it's low prevalence, then they're going to be pretty similar anyways. I'm a little behind on questions here. Where is the... So what's the question here? What type of disease that is communicable can be gotten without exposure? Wouldn't the exposure rate of the infected always be 100%? So no, the risk of getting a disease communicable or non-communicable is, unless it's a really brutal exposure, generally not 100%. I mean, in communicable diseases, we could talk about the risk of HIV given certain risk factors.
What type of disease can be gotten without exposure?
If there's like
Can be gotten without exposure. Well, if there's no exposure, then we're not going to talk about risk ratios or odds ratios.
Which is easier because they're all communicable. But if you look at non-communicable diseases and you have genetic predispositions, and that's without exposure to like
eating bad food.
Right,
But
or
it's
she's
not like
also,
sun exposure and cancer.
there's an assumption in this question here that we're observing all of the possible exposures, or that there's only one possible exposure. So, so you can have individuals who get the disease without the exposure, either because you don't know all of the possible sources of exposure, or because your exposure variable is not perfect. You just, you know, you don't know that exposure completely. So, an example would be multiple partners or unprotected sex for HIV. Another example would be, I don't know, with Ebola coming into contact with an infected patient. You have not a, well, I guess that's not a good example, because you will not have it without that exposure. That's an example of something where you cannot contract the disease without that known exposure. But it,
Is like genetic factor, is that exposure or like a predisposition?
that's a
right?
predisposition.
So that would be an example.
Mhm.
Right, but it.
So,
yeah,
but
that's
in,
an assumption.
for most diseases, there are a number of different possibilities for exposure, and you're just going to look at one of them. Or you're going to look at an incomplete information about exposure to the disease. So, lung cancer, smoking, well, that's a non-communicable disease. HIV, multiple partners. There's, in general, your exposures are not just no possibility of getting the disease to some possibility. They're a potentially lower risk to a potentially higher risk. When in public health, do we use odds instead of risk? I guess we've covered that now. We use odds ratios in case control studies. We use them in logistic regression. We use them pretty commonly. In fact, I don't know, in my line of work, they're much more commonly used than risk ratios. I think that in cohort studies, representative samples, risk ratios are often used because they're a little easier to interpret. Oh, please ignore, okay. Well, I got a bit behind here. One specific exposure source, yes. In general, we could look at multiple exposure sources by doing more than a 2x2 table. But so that chi-squared formula does not have to be for one exposure source only. You could use it for multiple ones. Odds instead of risk. Okay, I think I've covered all of these now. Uh-oh. Okay. So the conclusion of this story about race and the death penalty, at least as far as this study went, was that they also broke this down by the victim's race. So doing this this whole table again, looking at so here we have victim's race and defendant's race. So defendant's race, white, black. This part of the table is the same, but only for white victims. Observed and expected. The let's see, the odds ratio here for white to black defendants is now in the other direction, 0.42, meaning that now the white defendants are, let's see, what was it in the other case? It was whatever, black, it was 2, so whites were more likely to receive the death penalty. Here they're less likely to receive the death penalty. And then the other case, there are very few, so in the case of, oh, but by the way, there were very few counts here. How many did we have? Oh, I guess not so small, 227.92. In this one, there are very few counts. So with black victims and white defendants, we have only 9 cases of the death penalty. What's that?
I was being sarcastic, but yeah, that's not really fun to look at. You kill a white person, you probably get a penalty. You kill a black person, you might get off.
Yeah, well, so looking at this table, that was essentially the conclusion here, that the independence is much more violated, or there's a much stronger association with the defendant's race than, or sorry, with the victim's race than with the defendant's race. So with
So, it's like, that looks way too nice for like statistics about black people.
so yeah, with white victims, there's a 6% application of the death penalty. With black victims, only a 1% application of the death penalty. Generally, in Florida during this period of time, it was more frequent for black people to kill black people and white people to kill white people, and this is essentially the source, or can be explained as the source of the difference. This is an observational study, so it's really beyond the realm of statistics to say what is the causal factor here. That's really into the realm of sociology and race studies. But what we can say is that the where there is a white victim, there is here a risk ratio of 6 for the application of the death penalty, very large, and the case of black kills white has by far the largest application of the death penalty. So it's 12.6% relative to black kills black, which is the lowest, 0.8%. So it's a good example, I guess, of how you can always be missing a variable in your analysis that might help, that might make this story different or more complicated than what you're looking at in an observational study.
What were the victims' rates? Do you consider here that confounder?
This I don't know, it would be hard to say what's a confounding variable here. You would have to know something about what goes on in those trials and in those, in those jurors' minds, I guess, to say what is the confounding factor and what's the causal factor. I mean, we could argue, we could talk about it and say, assuming that victim's race is the causal factor, then is defendant's race, is that just a confounding factor, or is that also a causal factor? We could think through that, but how are we doing for time? Oh, 6:03. Okay. Some conclusions from this study. The race of the victim was more strongly associated with death penalty than the race of the defendant. 95% of the white suspects were indicted for killing whites, and 86% of black suspects indicted for killing blacks. And those suspected of killing blacks are rarely sentenced to death. So if victim's race is a causal factor, then defendant's race is sort of merely associated with, it is possible that defendant's race is simply an association with victim's race, but we of course can't make causal conclusions from just on the basis of these data. Oh yeah, as I mentioned, it's an example of a statistical interaction here between victim's race and defendant's race, and this sort of confounding conclusions from the data. Almost done here. Here's some related tests to the chi-squared test. McNemer's test is for paired samples. That would be the equivalent of like the paired t-test for paired counts. The exact binomial test would be the equivalent for small samples, even though the Fisher's exact test is often used for small samples. I don't think of it as an alternative to the chi-squared test because the null hypothesis is different. So it depends on your study design whether Fisher's exact test is appropriate or not. It's different because it assumes that the marginal totals in your table are fixed. And the example that was actually the original example that R.A. Fisher used to explain this exact test was a lady given 10 cups of tea. 5 of them have milk added before the tea and 5 have milk added, and she claims that she can tell based on just the taste what the order it was. Now if she is told that 5 have milk added before and 5 after, and she correctly identifies all 10, what is the probability of that happening under H0? That is the scenario for Fisher's exact test. That is not the scenario in the race and the death penalty case because there's no experimental design fixing the margins. Like there's, it's an observational study. So I've heard Fisher's exact test described as it's a test that gives you an exact p-value to a different question. But I don't know, it's so widely used that you can probably get away with it. And you'll probably have people tell you to use it when you have too many small cell counts for a chi-squared test. Does that make sense? The difference between these two setups, between the null hypothesis for the chi-squared test and the null hypothesis for Fisher's exact test? Can you see why the margins are fixed in this case? So you can imagine that with fixed margins, all of the possibilities, so in these tests, you're calculating the probability of getting an observed table of counts as extreme or more extreme than what you get from your sample. And that depends on what all of the possible observed values are. In the Fisher's exact test, there are fewer possibilities because all of the possible ones have to add up to the same amount in the rows and the same amount in the columns. So in this case, the sum of the rows have to be 10 and the sum of the columns have to be 10. But under the chi-squared test, that's not an assumption. You could have all 10 of them. You could have 10 in one column and 0 in the other column, for example. It would be like not telling the lady that they're 5 and 5. So she might, under the null hypothesis where she has no idea, she might say all 10 of them had milk added first. So there are just more possibilities under the null hypothesis of the chi-square test.
But if it's not a fixed marginal total, it can be a binomial test.
Right.
Right.
Yep. If it's not a fixed marginal total, it's a binomial test, and chi-squared is just an approximation to the binomial test. All right, so just a quick wrap up. These are for two categorical variables. They can be binary like we did today, or they can have more categories. That's fine. The tests are the same. The null hypothesis is independence. It's a two-sided test in that departures in any direction from the null hypothesis can give you a small p-value, even though the test statistic is just one-sided. Type 1, type 2 errors, they're the same. And I want to get you down reasonably early to the lab because we're going to be going and hearing from someone from the Department of Health today. So I'll see you down there.